So hello, wherever you are, we are very pleased to open this networking channel session. We started more than 3 years ago. It was on March 24, 2021. And we would like to thank you for your contribution and your participation. And today, we are very exciting with this special session, which is dealing with next generation networks, heterogeneous ones, and how they will be supported by evolving AI architecture. So without further ado, I'm very pleased to hand over to Marco and Dan, who I would like to thank warmly for taking care of this session. And again, thanks to everyone for joining.
Thanks, Sergio, for the kind introduction. Hi, everyone. So this is Marco Ruffini. I'm a professor at Trinity College Dublin. I'm here with my co-chair, Dan Kilper, who's also professor at Trinity College Dublin, and we have 3 panelists today. So as Sergio introduced, so we're going to talk about how AI architecture will further develop as they get introduced more and more into 5G and 6G network, and especially, how we might be moving from a single domain implementation to a multi-domain implementation that supports disaggregated end-to-end AI. So again, today I'm joined by 3 speakers. So we'll have in this order, Anna Tzanakaki, who's professor at the National and Capodistria University of Athens. Then we will have Luiz Silva, who's director of the Commonwealth Cyber Initiative and professor at VirginiaTech. And then we have Vadim Sheinin, who's a distinguished researcher scientist from IBM. Now, I'm gonna first I've asked Dan Kilper to give a quick introduction, an overview on this EU-US funded project called CGXL, and which is the project where the ideas from this webinar have come from. So I'll give the floor to Dan. So Dan is co-chair of this webinar, and is also director of Connect, and is professor at Trinity College Dublin, and will present CGXL.
Yeah, thanks, Marco. Hello, everyone. Let me get my presentation started here. Let me swap my video here. Can you see, you're seeing the presenter view or the? Do you see
you
my?
Can go ahead, Dan. No, it's perfect. Please go ahead.
It's perfect. Okay, perfect. Okay, yeah. So thanks so much. So delighted to be here today, talk about AI and 6G, and we wanted to introduce the 6GXL project, which is helping to organize this event. And 6GXL is a 6G SNSJU funded project in the EU, and it's part of the EU-US cooperative research and innovation program, where basically we're trying to bring together researchers from across Europe and the US to work on this really interesting topic. And basically we have 10 EU partners, and we've identified 10 US collaborators. And importantly, we're bringing together 9 major initiatives across the EU and the US. And this project, it's interesting. It's sort of half a project that is about cooperation. It's about bringing together test beds and initiatives and working together on how we should work with AI for 6G. And then also it's a seed research project where we'll be doing some research to basically develop a framework for working with AI in 6G. And I'll tell you a little bit about what we mean there. So first off, we identify that there's this fragmented environment of when you deploy AI, and today when we do a lot of research on AI, there's many different technologies involved, and we can talk about AI algorithms that are communicating sort of north-south between the devices through to the data centers and the control planes, and the upper layer, sort of across the layers. And then also there's kind of an east-west sense where you might think about an AI algorithm that's working across radio and optical networks, so multi-network, or across different operator domains, right? So a multi-domain type network. And this is a challenging environment to implement AI if you want to do it in a practical scenario in a 6G environment. So what we're looking to do is to develop an AI framework for thinking about and controlling AI for future 6G networks. It's not that we want to build a prescriptive controller that everyone has to use, but that we want to build a framework for AI controllers that can work across the radio environment, so in different RICs, as well as in the sort of transport SDN and network OS operating system type environment, and see if we can define common elements and really try to study and explore the interfaces and how to make AI work across this type of environment. And that's basically it's a decentralized, multi-party, multi-network AI framework that we're developing. So that's it in a nutshell. And we please visit our website. And if you're interested to get involved and work with us on this problem, we'd be delighted to talk with you. And one of the things that we want to do is to stimulate discussions around how we should use AI in 6G and what that is going to look like. And that's what we're trying to do here today. So looking forward to the discussion today with the panel. Okay, thanks, Marco.
Thanks, Dan. Okay, so we now, I think we go to the first speaker of the panel. So the first speaker is Anna Tzanakaki, who's an associate professor at the National and Capodistria University of Athens, and the leader of the Systems and Network Research Group. Her research interests include network architectures and design that over the past 10 years have focused on 5G and 6G infrastructures. She's been involved in a number of EU collaborative research projects and has served and is serving as the technical coordinator of various EU projects, including 5G Picture, 5G Victory, and 5G Tactic. She's co-author of over 220 publications and a co-inventor of several patents. And now I give the floor to Anna.
Hi, hello. Thank you, Marco. Thank you very much for the introduction. Thank you both, you and Dan, for the invitation and the opportunity to give this presentation here today and be part of this panel. I'm hoping that my presentation is shown okay. The slides are shown okay, right?
Yes, excellent.
Yes,
okay,
yes.
Great. Okay. A very short motivation behind this discussion. The talk will focus on how AI can be an enabler for 6G services, trying to understand a little bit the context of 6G. It's expected to support a large variety of applications and offer improved performance in terms of a number of key performance indicators when compared to 5G, so peak data rate, latency, energy efficiency, device density, and so on. An important aspect of 6G is, in fact, to introduce, to embed increased intelligence and flexibility, and this can only happen through wider adoption of artificial intelligence and machine learning techniques. 6G will offer ubiquitous infrastructure, integrating the most advanced network and compute technologies in a flexible and scalable manner. And in this context, networking technologies, advanced networking technologies, like, for example, optical networks, would play a key role. But the problems we have to solve relate with increased complexity. So we have to integrate these heterogeneous domains, cloud, edge, far edge computing. We need to integrate together different networking technologies. We have to deal with big data and data analytics. So, and another aspect would have to be with the support of vertical industries and different services associated with vertical industries that will require the creation of dedicated slices across the various domains of our infrastructure. And this can happen with features like programmability through softwareization, virtualization, open sources, and open interfaces. And in this context, we need, of course, to find solutions for end-to-end orchestration, management, and control in order to provision end-to-end services and in accordance to the quality of service requirement of the associated services, which require enhanced concepts and methods and technologies. Okay, if I try very briefly to show you at least our understanding of the overall architecture of a 6G network, what you see at the very bottom, and I don't know if you can see my cursor or not, but at the very bottom, the layer at the very bottom indicates the user, the data plane, involving different deployment options of the RAN, monolithic, disaggregated, and of course, requiring a a transport network interconnecting the different parts of the RAN deployment and the core network. And on top of this, you see the network infrastructure control layer, the network service layer, and on the very top, the control and management layer. So it's a multi-layer architecture required to provision services over a multi-technology data plane. And in order to be able to support different deployment options that are absolutely relevant in 6G with regards to the RAN and the core, we need to consider and address issues of the placement of the different 5G elements, the remote units, the distributed units, the central units, and so on, across different locations in the network. And in this environment, we need to then address the point of end-to-end orchestration that I briefly mentioned before, which will have to interact with different building blocks of the system, which can be quite complex, as indicated in the figure. Okay, now if we try to draw an architectural diagram, taking also the compute perspective, one can draw a diagram that looks like this, where you can see the different RAN domains and the core domain interconnected through transport network solutions. And this, as we already discussed, involves various technologies. One that one expects to play a significant role, of course, is optical networking here, but other technologies like wireless or Ethernet type of solutions, packet-based solutions, of course, will also play a role. Now, on top of this, we have the management plane that allows the control, facilitates the control through the domain-specific controllers. And we talk about a distributed control plane that allows distributed control plane operations. Of course, within each domain, we have the capability in the context of 6G to support distributed AI and machine learning functions. And it was also, I think, mentioned by Dan in his talk before. So these little blue boxes that you see here are embedded AI type of capabilities that are associated with specific domains. Now, to enable the interaction of our system with these AI elements, we have this intelligent cognitive plane on top of the management plane, and what we call a machine learning function orchestrator, which allows the combination of machine learning functions in order to be able to support the optimized 6G services, taking advantage of the capabilities of these elements. And this is now controlling or communicating with the end-to-end orchestrator, helping the end-to-end orchestrator to take optimal decisions with regards to resource allocation in support of service provisioning. So this is a fairly complex architecture which allows us to support distributed 5G functionality that can be embedded in different network domains. And this can be different network, but also administrative domains in some cases, taking advantage of distributed machine learning functions that can be present in different in these different domains in also a distributed kind of way. Now, this is a very complex environment which clearly introduces the need for autonomous operation. So we need to develop novel technology solutions that allow each layer to operate in an autonomous operating mode. And here you can see the different domains, for example, different RAN, transport network, core network domains. And we also see different layers operating in an autonomous kind of way. But of course, all these different elements, whether these are different domains or layers, they have to operate independently, and the functions within each domain are not visible to consumers, but they also need to gracefully interact between them. Now, our more recent work and relevant proposal is focusing on intent-based networking. So what we propose to do from a technical viewpoint to support this requirement is to adopt the concept of intent-based networking, And what that does, it transforms a hardware-centric manual network into a controller-led network, and which captures business intents and translates them into something that the network can understand, into some kind of policies. And then this can be automated and applied across the network. So we have a software-enabled automation technique, which combines machine learning, AI analytics, and orchestration to improve network operations and uptime. Okay, so here you can see the structure in a little bit more detail. So we have this interface here, which is used to introduce content within the intent framework. This provides the way to insert information from the vertical industry manager and identify the specificities, bring in the specificities of the vertical sector. This information is inserted into the intent framework, so we collect the intent, and then this is translated into network-specific requirements. Then the translated intent is sent into the network controller using specific application programming interfaces, and these can then control the underlying infrastructure and support the delivery of the network services. Specifically how this can happen, at the business layer, we have the implementation which allows the submission of the business objective, so we can have some kind of human or vertical input in the form of text or voice, which is then translated into domain-specific information, and this happens through the so we have to produce some specific programming language parameters, and this happens through the natural language processing. This functionality, in an example we have worked with, is implemented using a translator AI model. So what happens is we have the input in the form of text or voice, which is then translated into, for example, an optimization model or some kind of configuration file to set up the underlying network. And through this, we get as output the specific network-related KPIs, for example, throughput, latency, and so on. The example we developed is based on the well-known paper from Ashish Vaswamy. And it's based on Transformers AI model. So we have our Transformers AI model, which comprises an encoder and decoder. The encoder is used to understand the semantic and syntactic language information coming from the high-level intent and then the decoder is used to generate the response that the network can understand. So an example we implemented was actually trying to set up an end-to-end slice across our 5G infrastructure using a high-level command that could, for example, come from a vertical in the form of, for example, some text saying set up an energy-aware URLCC slice. The Transformer AI models generates the appropriate optimization code to be used to identify the corresponding URLCC slide. How does this happen? The high-level input we have is the intent, is the sentence saying set up this end-to-end energy-efficient slide, and the output is identifying optimization code out of a library of a selection of code that is the optimal code to use in order to set up to identify resources for this end-to-end slice. Now, how we identify the optimal code, this is through correlation. So identifying this, maximizing the probability that correlates the high-level intent with the capabilities of the code. And here you can see some of our results. You can see the sentence here, the high-level intent here, and the different functions of the code and the degree of correlation it can be shown through the color of the blocks here. So we can identify through this the optimal code to use, optimization code to use, and we also tried an example by changing the syntax, slightly changing the syntax of the sentence into create URL slice energy aware, and again you can see that the results we achieve are quite similar. So the optimization output is now used by the service layer to auto-generate relevant configuration files for the UPF node. So, okay, we have now identified the resources and we now need to set up the resources so they can support the service we're after. So we need configuration files to be produced to configure the UPF nodes. And then we also go into the transport network specific configuration. So the translator generates the command and configuration files in order to establish the transport network connectivity. And then we applied this approach into a 5G testbed, real testbed we have in our lab. So we have our 5G testbed, which you can see here with open source Mano on top. And we applied this intent-based approach on top of this infrastructure. And we were able to provision, to instantiate two different slices across the infrastructure. So you can see here the two different slices that were produced and instantiated across the 5G infrastructure. These particular slices share one common core network, but they go through different transport paths, and they also go through different UPF nodes. To conclude, we have been looking at 5G and 6G architectures, and it's clear that there is, due to the complexity of the systems, there is a clear need for some autonomous operation. We have proposed the adoption of intent-based networking where AI plays a key role. Of course, the solution I mentioned is in alignment with generative AI approaches. So I showed you an implementation example of an IBN, of the IBN approach over a 5G infrastructure where we performed end-to-end slicing, enhancing and orchestration, the orchestrator with the IBN capabilities. So thank you very much for your attention.
Thank you, Anna, for your presentation. I just remind the audience that we're not stopping for questions in between the presentations, but you can. There is a Q&A section where you can start piling up your questions, and the panelists will answer those at the end. We'll organize a panel session at the end. Okay, so the second speaker of today is I'm going to introduce is Luiz da Silva, who is Executive Director of the Commonwealth Cyber Initiative and the Bradley Professor of Cybersecurity in the Department of Electrical and Computer Engineering at VirginiaTech. His research focuses on distributed and adaptive resource management in wireless networks, and in particular, cognitive radio networks and the application of game theory to wireless network. Luiz was at the Telecommunication Society Distinguished Lecturer and is also a fellow of IEEE for contribution to cognitive networking and to resource management in wireless networks. I give now the floor to Luiz.
Thank you very much, Marco. Let me just share my slides. Hopefully you can see full screen of my slides.
Yes, perfect.
Great. So thanks, Marco, and thank you, Dan, for the invitation. VirginiaTech and the Commonwealth Cyber Initiative, or CCI, are part of 6G Excel, so we're very happy to be in this webinar as well. As Marco mentioned, I'm a professor at VirginiaTech, and I lead what's called the Commonwealth Cyber Initiative. And today I'm going to talk specifically about some of our work on open radio access networks, or ORAN. And before I do that, let me just very briefly explain what CCI is. So the Commonwealth Cyber Initiative is a consortium of 45 higher education institutions in Virginia. So private and public universities, as well as community colleges throughout the state. So the map that you see is a map of Virginia. And all of these universities and colleges work together with a common mission of making the Commonwealth of Virginia a globally recognized leader in cybersecurity. And we do that through innovation, through workforce development, and through research. There's about 350 professors involved in the initiative throughout all of these universities and colleges. And more relevant to today's topic, we, from the get-go, when we thought about research in cybersecurity in Virginia, we selected a few areas of focus. And one of them is looking into the next generation networks. So 6G, some into 5G, but really looking at it is variously called next G or 6G or future G. So what comes next? And of course, no one knows exactly what 6G is going to look like, but the visioning exercise for 6G is currently underway. And one thing that's always mentioned is that 6G will be AI native, right? So AI will be incorporated from the beginning. And of course, we believe that's very important that it also be secured by design, so that security be incorporated in every aspect of 6G, including the use of AI, as well as some trends in terms of the architecture of the network, including disaggregation, virtualization, and softwareization. And we also look into how to manage this increased complexity that comes from the evolution of mobile networks. And then one other area of research that we identified for CCI is artificial intelligence. So, and then basically two aspects. So how can we use AI to improve cybersecurity, not only in the context of networks, but more broadly? And also, how do we secure systems that rely on AI? So we call this AI for cybersecurity and cybersecurity for AI. Okay, so we identified these two areas of focus. There are a few other areas that we cover in CCI, things like supply chain security, inclusive security, etc. But those two areas, of course, have a big overlap. So both in the use of AI and how to we secure the use of AI, and then in the incorporation of AI into 6G architectures. So one way that we started working on these problems is through experimentation. So we have researchers who are more in the theoretical side of the topic, some that are more doing simulation, some that are doing more hands-on research. And we decided to build an open testbed for experimenting with these different architectures and different technologies that are expected for the next generation. And we call this the XG testbed in CCI. And because we are interested in, first of all, research, but also specifically in security research, we need the researchers to have access to the internals of the network. So we ended up building the testbed out of completely open source components. The testbed also incorporates some commercial hardware and software, but the core of the testbed, or the basis of the testbed, is all open systems. So in terms of hardware, we use a lot of software-defined radio front ends, and specifically the USRPs, various models of USRPs. And then for the software, we rely on SRS-RAN, as well as Open Air Interface, and then OpenStack and Free 5G Core, and other pieces of software to put together this end-to-end system. To support the incorporation of AI and machine learning, we use Akuma's AI, as well as Kafka and ClearML as the basis for incorporating machine learning and AI solutions and data flows into the network. And then we embrace open standards. So as we were building this testbed, it became clear that the Open RAN interfaces being defined by the Open RAN Alliance would be an important aspect of that. So we ended up joining the ORAN Alliance in 2021. And then eventually, 2 years later, last year, we were designated as an Open Testing Integration Center, or an OTIC. There are about half a dozen OTICs in the US and another as many in Europe and in Asia. So these are testing integration centers that were designated as such by the ORAN Alliance, where we are bringing in ORAN compliant equipment and software solutions and testing them, both in an indoor facility. So the top picture shows part of our indoor test bed, which comprises about 72 nodes. These are USRPs, X410, X310, B210, and etc. Including a lot of processing power, so GPUs and CPUs to run the actual radios. And then we have an outdoor version of the test bed, which the picture below shows, which is a 1.5-mile corridor in Blacksburg, Virginia, in Southwest Virginia, where the indoor test bed is actually in Arlington, Virginia. The two locations separated by about 250 miles. And so that allows us to also experiment with a cloud-based solution where parts of the network run in a cloud in Arlington, and the radio access networks connect to it from Blacksburg, Virginia. We also announced a partnership with SRS Systems, which provides both a full stack 4G and 5G solution, and we're a member of the NextG Alliance, which is a North American consortium looking at the visioning for the next generation of networks. And actually, one of our professors acts as the technical director for the NextG Alliance. Okay, so we've been building this test bed. It's right now providing a fully ORAN compliant solution end-to-end. And then specifically on the topic of an AI architecture for that, we follow the specifications of the ORAN Alliance and then build a control loop solution that complies to those specifications. So this is kind of a view of that solution. So we have X apps in our apps developed, so both the non-real-time and the near real-time RIC supported here. So the X apps do things like load distribution, steering traffic to a particular area of the network, quality of service optimization, the monitoring of relevant key performance indicators. And then the R apps do things like load balancing across the network, prediction of KPIs that are associated with particular flows and services, energy saving types of solutions, and then monitor the virtual network functions within the network. We also built some some software to monitor both the operation and the functionality in the near real-time RIC and the non-real-time RIC. And then we have an SMO that manages this whole system. One example of this use is something that we demonstrated a couple of times now, but the last time we did it in IEEE Infocom last year, which is the use of the non-real-time RIC to do some resource management and to monitor different classes of traffic on the network, and based on the monitoring of that demand, use machine learning to infer what kind of resources are required to support the different types of applications. There's a training agent that keeps working on the data that is generated in the network, and that actually drives the assignment of resources in the network, so resource blocks and so on, to particular applications. And we implemented that, and we showed it, as I mentioned, a couple of times at the Mobile World Congress Americas in Las Vegas, and then last year at IEEE Infocom about a year ago. So the picture tries to show the entire system, right? So there are 3 dashboards. Two of these we developed, and then one we adapted from an open source dashboard that already existed, and we revived that project and enhanced it, so that we can monitor the operations of both the non-real-time RIC and the real-time RIC. We have 2 types of UEs. So sometimes the USRPs, which you see on the table, they act as UEs, and then sometimes we use actual commercial smartphones that you also see on the left-hand side of the picture as the UEs. And then we have various devices acting as the base station and hosting both the non-real-time and the real-time RIC. And what we show here is the coexistence between a highly demanding, high priority service for example, first responders, coexisting with a more everyday type of use of the network by subscribers. And what the AI does is it keeps monitoring the 2 types of demands for service, and as the demand for the high priority first responder service increases, it redirects some of the network resources, so some of the resource blocks to that use, without completely starving the regular subscriber. These solutions, the RAN part is all using SRS solutions, so both for the UE and the RAN. And then the core is using an open core solution as well. So we have a short paper that describes this demo in more detail, in which the reference is here. We did an evolution of that at the Mobile World Congress in Shanghai last year as well, in which the demos were all online. So there's a video associated with that, which I'll be happy to provide a link to. And then we have a little bit more theoretic work that looks at the use of AI to also optimize the deployment of the near real-time RIC functionality on a distributed cloud infrastructure, where you have multiple sites distributed geographically. So in this case, in Northern Virginia, where I sit, and in New York and in Miami. And we have a solution that automates the placement of the near real-time functionality to minimize costs constrained by meeting latency requirements from the near real-time RIC. And what we show in a nutshell is that in this cloud-native environment, this disaggregated near real-time RIC and being able to place the functionality according to the constraints on latency, but also the cost and availability of resources, provides a cost savings around 60% as compared to a more monolithic approach. This work is appearing in the IEEE Transactional Network and Service Management this year, so there's a preprint available through the IEEE Explorer website, as well as my own website. All of this work on O-RAN, which incorporates AI into the solutions, I think is going to be turbocharged by some investments from the US Chips and Science Act. So some of you are, I'm sure, aware that the US Chips and Science Act provides $1.5 billion in investments for what's called the Wireless Innovation Fund. And the first 10% of those funds were distributed according to a call for proposals in the end of last year and beginning of this year. So there are $150 million in research funding was awarded to various groups. VirginiaTech and CCI are part of 6 of those projects. There are 2 classes of projects, some that look into research and development. Those are $2 million projects, and those are the last 5 that I listed on this slide. And then there are some larger scale projects for testing and experimentation. And we are part of one of such large scale projects that is led by AT&T in cooperation with Verizon, and where our test bed in Northern Virginia is one of the anchor test beds for that project. So all these 6 projects, and there's another about maybe 8 or 9 or 10 projects that were awarded in the last few months. They all have to do with actually showing that ORAN is viable and that provides performance and security and scalability that is needed. A lot of them touch on incorporating AI as part of the architecture, so I think are relevant to this discussion of evolving AI architectures towards 6G, and they're something to keep an eye on because it's a big investment from the U.S. federal government into making AI AI within the next generation of networks, of open networks, a reality. So the picture that you see is the U.S. Commerce Secretary Gina Raimondo at our facilities at VirginiaTech and CCI in Northern Virginia, announcing the latest of all of those investments, which was this $42 million project. There's expected to be another call for proposals, another notice of funding opportunity issued in the next few probably weeks by the NTIA that will providing additional investments as part of the Wireless Innovation Fund. And then I just wanted to mention that one of our areas, as I mentioned before, is AI for cybersecurity and cybersecurity for AI. It's broader than this discussion of AI within networks, next generation networks. It really applies to other areas as well. But of course, a big area of focus for us is AI as a component of networks. So we look at things like data poisoning attacks and minimum perturbation and what kind of disruption that can cause, denial of service, ransomware, etc. And one recent example is some work that we have done in the context of ORAN on a possible denial of service attack that takes advantage of the E2 interface to mount this denial of service, and then the use of XApps to monitor latency and traffic and to be able to detect such an attack as well and react to that attack. So this kind of work, we end up working closely with the ORAN Alliance to make it known to them that there is this vulnerability that needs to be fixed. I think that's all I had. So thank you very much again, and I look forward to further discussions.
Thanks, Luiz, for your presentation. And so we're running a little bit late now, but we're going to go straight into the next speaker. So then our next speaker is Vadim Sheinin, who's a distinguished research scientist from IBM Research, working in the area of generative AI and its application to code generation and networking. He worked on various compression algorithm systems to be used in telephone networks, including voice IP, as well as image and video processing implemented on architectures with high parallelism. Vadim's recent work explored foundation models for 5G radio access network optimization. And please, Vadim.
Thank you very much. Thank you for the introduction, Marco, and the invitation. I'm going to talk about network foundation models for RAN optimization. We've concluded recently a POC with a major telco provider in US along these lines. The goal was to explore network foundation models for telco, and the use case was along the lines of RAN optimization. RAN optimization obviously is very important for the providers, and we have two objectives. I will go a little bit fast because we have not much time. Two objectives. The first was the kind of warm-up objective, which is to predict downlink throughput. And the idea was to compare performance of foundation model, and I explain later what I mean by foundation model. To compare performance of foundation model with the traditional machine learning techniques, in particular XGBoost, in prediction accuracy. And the second main objective is to answer the question how to use foundation model-based approach to optimize network quality of service, let's say, by turning certain parameters, tuning certain parameters. We got drive test data from this provider. There were two different parts, drive test and brand data, but both of them were recorded during drive test. 4 different metros, about 2 years worth of data. Measurements, whatever is recorded during drive test, configuration parameters, everything that is exposed during drive test, or everything that can be recorded during drive test, we got this data. They were in particular very much interested in the handover and how to optimize handover parameters. So in this picture, you can see a typical handover scenario where, let's say you're connected to tower A or cell A. This is the serving cell. It's a 5G architecture. That's the blue curve, right? And let's say you're driving away from their current tower that you're connected to, right? So the quality of the signal will decrease. And you are also monitoring all the neighboring cells, you being UE, right? You're monitoring the quality of the neighboring cells, and let's say tower B, you are driving towards tower B, and obviously the signal is increasing, right? So when the power of the reference signal coming from the neighboring cell is a certain number of dB higher than the signal coming from the serving cell, UE will generate an event, which is called A3 event. And then the network will decide whether to initiate the handover or not. And so there are various events here on the left related to handover. And so they were interested in understanding how to weaken those parameters will give them the best performance. We've developed a pipeline, traditional pipeline for our foundation model, which in this case is a transformer-based encoder-only model. We start with data preprocessing, where we had to merge the data sets. We had to perform a feature selection because we started with the 2 data sets. After merging, they had more than 1,000 columns, right? 1,000 different parameters and measurements and so on, and about several million rows. So every second or so, everything is recorded, right? And so you can think about it as tabular data. Tokenization, where you need to deal with numerical data versus categorical data. And then we did the pre-training in the same same fashion as traditional LLM, mask language model, MLM. So you can think about LLMs taking a sentence and eliminating 10-15% of tokens and forcing the model to predict those missing tokens, right, during pre-training. So we did the same during pre-training, except we are not given a sentence. Obviously, we are given a row from our tabular data, right? And we had several millions of those. And then after pre-training, you can do fine-tuning for 2 tasks, one being regression, where you want to predict numerical value, and another being classification. And I'll show you examples of those. And so comparing foundation model approach, and this model had, it's a Roberta model, so 120 million parameters. It's a tiny model. And we compared, as I said before, with XGBoost. And so by predicting, or when predicting downlink throughput, which is one of the measurements performed during drive test, we achieved R-square about 20 percentage points more than XGBoost. So an XGBoost for the same data, right? So XGBoost performed 72% R-square, or 0.72, and for foundation model we got 94%, 0.94. That was R-square, and And for the classification, we chose to look at handover attempts, which is one of the categorical parameters there. And the data showed that we had values there from 0 to 4, 0 being no handover was attempted at a given row at a given timestamp. And from 1 to 4 is the corresponding number of attempts. And so we used macro F1 as a metric for a certain data set. We use certain data set for XGBoost, the same data set for foundation model. And we got better performance somewhere between 5 to 13% improvement in F1. And so the conclusion of this POC was, okay, we know how to build a foundation model that can be used as a great predictor. The question is, how do you use it in telco scenarios, right? So we came up with several use cases where we think foundation model is instrumental and will bring some goodness. So one of them, for example, is bad cell identifier. So let's say we fit the configuration of a certain cell into our foundation model, and the model predicts certain KPI, throughput, uplink, downlink, some KPI, let's say it's 10 megabit per second is the result of the prediction. And let's say the core network itself measures less than that. So for example, 5 megabit per second, right? And so then we will say, okay, something is wrong with this cell, because if you trust your predictor and you say that based on the configuration, you were supposed to see 10 and you see 5, then something is wrong. And engineers can pay more attention to this particular cell. That's one. Use case number 2 is optimal configuration parameters identification. Imagine that using only pre-trained model, you can feed. So let's say somebody wants to configure certain cell with certain set of configuration parameters. For simplicity, let's say 10 parameters, right? And so we can take 9 out of 10, feed them into the pre-trained model and ask the model to predict the missing one. And we can do it for all 10, one by one. And if the discrepancy or difference between the predicted one and what was planned to feed into the cell, right? If the discrepancy is small, then we say, okay, it's okay, and no problem with this configuration parameter. And if discrepancy is large, then we say, you know what, for this neighborhood, for this context, for this 9, this particular one, which is number 10, is out of order, kind of outlier, right? So we could predict potential anomaly in configuration. That's one. And also we could see which parameter is responsible for the low KPI. So let's say network identified low KPI. We could actually see what configuration parameter or what sets of configuration parameters can be responsible for the low KPI identified by the network. Another interesting application is saving cost and time for pre-deployment scenario of new base station. We know that telco operators spend a lot of time/money on before deploying a new base station, a new cell, right? There are certain procedures that they need to go through, which are lengthy and costly. And so we could actually take the configuration, intended configuration, feed it into the model, see the predicted KPI. Network engineers can look at this predicted KPIs, and they see that it's roughly on par with what they expected. Then we say this configuration is okay. If it's not, then they can use the model to tweak the configuration set until they get what they want. So that would be faster. And every time, you don't need to go do drive test after you change configuration. We can use the model for that. And the last use case is optimization of these configuration parameters. As I said in the beginning of the presentation, that was the major use case. So the question was how to use a foundation model to solve optimization task. Well, foundation model is a predictor, is a classifier, it's not an optimizer. So the way we suggest to use a foundation model is as depicted here in the optimization loop. So everyone has certain optimization loop today, right? They have an algorithms that calculate how to adjust certain parameter. Then there's a measurement to see the effect of this change or performance evaluation, right? Whether it's drive test or some other techniques. And then based on what they've observed, they tune this parameter, they tweak, they turn this knob left or right, more or less. And so to make things faster, they can use foundation model as a simulator of the network, right? So if you trust your predictor, then you can say, okay, I build a network simulator or cell simulator, right? And you can use this simulator inside your optimization loop and reduce cost and increase time of deploying new cells, new network elements. I believe that's it. Thank you very much.
Okay, thanks, Vadim, and I'd like to thank the three speakers. So we have some time now. I think Sergio has granted me a little bit more time, so I'm allowed to go a little bit over time. So I'd like to call again all the panelists as well as Dan as a co-chair, and maybe we ask a few questions to everyone. If the panelists, guys, if you want to turn your camera on. Okay, thanks. So there's been a few questions, and thanks for the panelists already to go there and save time and answer the question directly. I had a question. So in general, I think there's an interesting thing that I've seen is that, I mean, all the panelists have shown that they've used testbed infrastructure for Open Run. And I think, so I wanted to know, you know, as we were told a few years back, you know, the XApps and ORApps and the Run Intelligent Controller was really the key of this new Open Run solution. And it seems that since 6G is going to be based even more on AI, you know, this is a natural evolution. But I just wanted to ask, you know, how did you guys find working with Open Run and the RIC? Is it something that you see a real benefit? Is it something that is feasible and it's something that will keep happening? Or, you know, it was an interesting experiment, but maybe not so much in the future? I think everyone is probably work on this. You want to try and give an answer?
So maybe I can start.
Yeah, thanks, Luiz.
Yeah, so it has been, I think, has been very productive in terms of evaluating how to incorporate AI into the management and running of the network. The one thing that we found is that we also had to train students a lot on this. So workforce development is going to be a big challenge, I think, as ON starts to get deployed as well. So we're trying to form a different kind of student who can actually work both understand both the network aspects and the AI aspects and the software development aspects and data management and so on. So that has been a learning opportunity, but it has been very productive so far. So we're very happy.
Okay, thanks, Luiz. Anyone else wants to jump in?
Yes, maybe I can also. Maybe I can also agree or emphasize the point. Well, we only have an early experience, and the truth is that the early deployments we have available have been proven to be quite challenging, and I think it was indeed a very slow learning curve at the beginning, but also the platforms that are becoming available now are a lot more powerful and much easier to use. So also for students, but also for effectively operators. I think the situation is improving as we go along. So the level of difficulty in operating these platforms is becoming smaller, I think. And the capabilities they offer increases, and absolutely it requires experience from a network perspective and understanding what AI entails and involves, which is a complex problem to deal with. So I very much agree, but I'm very optimistic because I start seeing new solutions coming up that are easier to work with.
Okay, thanks, Anna. And Vadim, from our side, I mean, you know, the application of the foundation model, were these things that were done to their run, to the RIC interface, or there are other interfaces on the network management that you think are more appropriate?
Well, actually, in our case, it was working with data only, data obtained from a telco provider, training the model, showing the performance, And we hope to go into the next phase with that provider, which will be using it in the field.
Okay. And maybe just as you are discussing about this, the foundation models, I was wondering, I mean, how accurate can the model become, and how variable does the model need to adapt to different networks, maybe in different areas or different scenarios? I mean, there is a constant training, or could be some transfer learning between areas or even between operators?
Right, a very, very good question. So in this POC, we used 4 cities, right, and 2 years worth of data. And so we built a model. We like the performance of this model, but I think it's a little bit too early to say that we can cover, any scenario. What we would like to see is a model trained on by far more data and by far more diverse data, and then see how it performs in the field in different scenarios. Then we can say, whether it's enough to have only one, or whether fine-tuning will be required per particular geography or feature sets.
Okay, thanks. So I know that we are running late, and the Serge wanted to ask a question to Dan as well. Dan, I don't know if you also have some other question. Otherwise, I think Serge has a question.
Yeah, I have a very short to Dan. As you said, CGXL is about enabling EU-US cooperation on that topic. So how do you plan to organize this dialogue? And how can people participate or contribute?
Yeah, so well, we want to work with organizations like Slices that are already organizing many kind of EU-US cooperative programs, especially in terms of conferences and events, and partner in there. And then one of the key elements of the project is that we're bringing together various test beds, and so the idea is that we want to create this framework that we can benchmark in the different test beds, and get the different test beds in the EU and the US working together to identify common ways of making measurements and implementing, say, an AI-based or an AI controller that would go into a RIC environment as an RAP or an XAP. And so then 2 test beds can deploy it in the same way, but then using their own use cases, using their own specific set of tools, and so how do we kind of get these test beds so that they can get similar answers and be looking at similar things and benchmark, even though they're inevitably using different sets of equipment and different problems that they're going after. So that's one of the key elements that we're trying to explore with this, and work with other partners like CCI at VirginiaTech, like the Cosmos testbed in New York, and we're eager to partner with others also in terms of collecting data and how we represent data across the different testbeds is a component of this as well.
Thank you. So anyway, I guess that the audience or whoever can contact you directly in case.
Absolutely. Please reach out, and we're happy to work with others as well. Yeah.
Excellent. So
Okay.
Marco, I guess we have to close unless you would like
yes,
to.
I think, yeah, it's been an interesting session. Thanks to all the panelists and Dan for co-chairing, and thanks for the getting answers on real work that's been done experimentally. Okay, so Sergio, I'll give then back to you to close the session and introduce the one for the next time.
Yeah, likewise, applaud to the panelists and the audience. Thanks a lot for taking some time to contribute to the community, to the networking channel. And I'm very pleased to make the announcement for the final session of the Spring 24 session, because as you might know, we have 2 sessions, one in spring and one in fall. So this will be the last one. Be careful, it's scheduled on May 22nd. So we'll have a short break in between, and it's going to be organized by Lily Q, and it's going to address another very exciting topic, which is about intelligent sensing and communication. So looking forward to meeting you again on May 22nd. Thanks again to everyone. Enjoy the day. Bye-bye.
Thank you, Sergio. Bye.
Bye-bye.